Can you imagine a more sustainable cement production process? In 2016, world cement production reached 4.1 billion tons, generating around 2.2 billion tons of CO2, equivalent to 8% of the global total CO2 production. Since then, the industry has been making efforts to reduce the environmental impact. However, it's still not enough. According to the latest report from the International Energy Association, in 2019 and 2020, 4.1 billion tons of cement were produced globally. Even with COVID-19 impact on the global markets, cement industry maintained the same production levels as 2019. And with these production numbers, 2.17 billion tons of CO2 were generated, representing a 1.5% reduction compared to 2016 numbers. Industry commitments with the international community are to reach 0.48 tons of CO2 generated per each ton of cement produced by 2030, which brings an ambitious target to achieve. Estimated cement production by 2030 will be approximately 4.8 billion tons of cement, with only 2.3 billion tons of CO2 produced, meaning that the CO2 reduction per ton of cement produced will drop 5.5% compared to 2020 numbers. Hello, I am David Salazar, AERZEN Regional Application Manager for Pneumatic Conveying Applications. Welcome to this interactive presentation, which is meant for you and me to participate and learn from some real case scenarios related to energy, CO2, and cost reductions in the pyro processing for cement manufacturing that contributes to achieve such an important target for the cement industry. Before we get going, let me ask you a question. Can you select the most accurate numbers to describe the energy consumption breakdown in the dry cement manufacturing process? Let's see the options. If you chose option A, you are correct. Boiling is the most energy demanding process, basically because it needs to reach temperatures over 1400 degrees Celsius. During the calcination process, most of this energy is thermal energy, in consequence, the highest CO2 emission producer. AERZEN is fully aware and committed to be part of this challenging target for the cement industry. We know that from those 2.3 billion tons of CO2 generated from the cement industry in 2020, more than 90% came from the calcination process. That is, of course, related to the energy consumption breakdown in the production process that considers both electrical and thermal consumption. This is why we will focus on that process optimization so we can learn the best practices doing what we best do, developing new business models and solutions for our customers. At AERZEN, since 1864, we design high-performance blowers, screw compressors, and high-speed turbo blowers for the industry. We introduced Europe's first positive displacement blower back in 1868. Since then, we have become a global player with over 50 subsidiaries around the world and more than 2,500 employees. Our goal is to redefine quality and innovation, so when you see an AERZEN name on a machine, you know exactly what you can get. You can expect performance. We're glad you've decided to join us in today's presentation. Agenda for the day include 3 cases involving real scenarios around optimization of the pyro process in a cement manufacturing plant. First, we will talk about raw material quality impact for high-quality clinker. Second, we will discuss some key aspects regarding burning systems. And we will mention the use of alternative fuels for clinker production. And third, we're going to talk about the combustion air process in detail. If you are willing to learn more about other applications or AERZEN services for the cement industry, you can also take a look to our specific application content in our YouTube channel. Again, thanks for joining us today and get ready for this interactive presentation. The case scenario we will be discussing today develops in a real cement plant, where AERZEN has been supporting different needs in after-sales and basic engineering advisory for the past 10 years, building a professional, strong, and trustfulness relationship that have granted AERZEN team to get involved in several renovation, expansion, and optimization projects over the past years. In order to have a better view of the topics we will be discussing today, here you can see the technical data from the plant. Cement industry, as mainly all other industries, require a raw mix to produce the final product, clinker, which is basically finished cement before it's grinded in the final milling process. Raw materials quality and the proper chemical composition of those materials are key factors to guarantee a proper burning process, avoiding lower heat transfer to bad quality batches. Raw material is as important as everything else in the process and play a critical role in the final product quality. Cement is manufactured through a closely controlled chemical combination of calcium, silicon, aluminum, iron, and other ingredients. Can you tell what is the composition range for a good quality mixture of Portland cement? Let's see the options. If you selected option B, you are correct. Raw mix for cement production needs to have a majority composition of calcium oxide and silica, and a lower proportion of aluminum and iron components. The percentage by weight included in the original mix is tested in the laboratory and needs to fulfill the ASTM C1157 standard classification, so it can be called Portland cement. Any deviation in the composition range, it's a valid construction material, but cannot be called Portland cement, and in consequence cannot be used for highly strength concrete applications such as buildings, bridges, roads, and so on. If we take a closer look to the last two materials showed in the chart, we see that the amount of material is represented as a minimal possible quantity and not as a percentage per weight. The reason for that is basically because the more magnesium and potassium we have in our mix, the harder the oxidation process will be, and we will see incomplete chemical reactions and bad clinker quality. Avoiding these two elements may not be as easy as it seems, as they are attached to the original stone. Corrective materials needs to be added and properly mixed to correct this problem from the beginning. However, it's impossible to avoid having some rocks with extra content of these two materials, which makes the work harder for the raw material milling machine that won't be able to pulverize completely the rock that contain higher quantities of these materials. In our customer's plant location, raw material is found with the following characteristics. Do you think they can use this raw mix to produce Portland cement? Clearly, they can't, which means they need to add corrective materials to guarantee the chemical composition before the raw mix enter into the process. The materials used to correct the mix depend 100% on the local availability and will change from plant to plant, even if they are located in the same country. As inland transportation costs are a higher price to pay, cement plants will look closely for the nearest material available. In this specific case, they use kaolin and clayey materials to add the expected minerals into the mix and overall reduce the amount of magnesium and potassium as arranged per weight in the mix to avoid major problems in the milling and burning process. All these materials needs to be properly mixed in the homogenizing silos, so the final composition is as smooth as possible and with the granular size needed to enter the preheater tower. Silos homogenizing and raw material pneumatic conveying to the preheater tower are two of the most important applications in a cement plant, where AERZEN equipment homogenize and convey millions of tons of raw material around the globe with our high-performing equipment. From the beginning of their operations, this plant uses a set of 10 AERZEN GM25S units to homogenize the mixture in 3 silos with a capacity of 12,000 tons. They had by the time a sliding vane compressor in operation to deliver pneumatically the raw material into the preheater tower. Operational conditions for those two processes are as follows. Late in 2017, a production increased demand required more raw material per hour for the process. As I mentioned, the existing machine was a rotary vane compressor that requires a fair amount of oil in its reservoir, a permanent water supply for cooling, and at least a year overhaul to guarantee the internal gap between the vanes and the cylinder to keep the same efficiency level. The machine was also operating near their operating capacity, and an upgrade wasn't that easy at the time. AERZEN team supported with the pre-engineering process and helped with basic calculation for the new pneumatic conveying capacity that the system required. The real challenge for this project was to increase the conveying rate from 2,700 kilograms per hour to the maximum capacity, maintaining the same piping system for the homogenized raw material. As mentioned before, for the type of material and density, the most common conveying method is dense phase, which basically means that the material travels at a slower speed, in general lower than 20 meters per second, on the bottom of the pipe from one point to another. The pipe diameter was an important restriction to the project. However, by increasing the volume flow by 50% and the pressure capacity 15%, we were able to increase line conveying capacity from 2,700 kilograms per hour to 3,500 kilograms per hour. Conveying speed also has an increase as more material needed to be moved through the pipe with the same diameter. However, we managed to stay at the lower 19 meters per second to avoid pipe clogging. Let's review some of the major takeaways from this case scenario in which we replace the sliding vane compressor technology with the AERZEN Delta screw compressor. First, 29% material handle increase, keeping the same major elements as piping, electrical wiring, footprint, and no major civil or mechanical investments. Second, keeping the same energy consumption, but increasing almost 30% the production capacity. And third, avoiding costly maintenance to oil reservoirs, water supply for cooling, and complete repairs to the sliding vane technology characteristics. Cement manufacturing is a highly energy and emission-intensive process because of the extreme heat required to produce it. Producing a ton of cement requires 4.7 billion BTUs of energy and generates nearly a ton of CO2. Different types of fuels can be used to reach that needed temperature to produce clinker, all of them with its cons and pros for the process, as well for the environment. Thermal energy is the most important part of the burning process, as the material needs to reach certain temperature to guarantee the proper chemical reaction of the raw material components. Can you guess how high is the temperature needed to produce cement? If you select option C, you are correct. At that temperature, bilites and calcites are completely formed into the clinker rock and having the appropriate microscopical shape that will guarantee that after the final grinding, where we will see the cement powder, water absorption will be even along the particle, which finally determines the quality and strength of concrete. Have you seen some cracks in the road? One possible cause is a lower cement quality. Now that we know how important is the temperature in the kiln, let's see the possible materials that can help us reach that high temperature. Do you know what is the most used solid fuel used in the cement industry? If you selected option D, you are right. Coal has been the most popular fuel in the cement industry for a long time. A wide range of other fuels such as gas, oil, liquid waste materials, solid waste material, and petroleum coke have all been successfully used as a source of energy for firing cement kilns, either on their own or in various combinations. As we know, clinker is brought to its peak temperature mainly by a radiant heat transfer, and a bright and hot flame is essential for this. High carbon fuels such as coal, which produces a luminous flame, are preferred for kiln firing. Natural gas is in most places cheaper than coal. However, the availability can be confirmed, and cement plants cannot afford to limit their accessibility to the fuel. Another material that has been widely used is petroleum coke or petcoke, an oil subproduct with similar heat transfer as the coal, but with a considerable higher CO2 emission per ton burned. In our customers' plant, they mainly use coal as a primary fuel source. However, as coal prices have had some considerable price fluctuations over the past years, and availability to the material has become a challenge in countries where power plants fired by coal are a priority. In addition to this, the plant was going through an important expansion project to increase capacity from 3.2 million tons a year to the existing capacity of 5.2 million tons. Taking this into consideration, the cement plant decided to increase burning capacity and make it suitable for alternative fuels and petroleum-based type of fuels such as petcoke. The existing burner, suitable only for coal and heavy oil, only for the startup, was replaced with a burner suitable for gas, liquid and solid fuels from different characteristics to include alternative fuels. The process required an important investment on engineering and optimization of the existing equipment. Let's take a look at how AERZEN supports this project. Here is the technical data. At the same time the plant was replacing the burner, new operational conditions were required for the fuel conveying system that considers both the plant expansion project and the alternative fuel condition. As in most of the expansion projects within the cement plants, piping was required to keep the same length and nominal diameter, as complete replacement will require a more complex intervention with a longer downtime. Biggest challenge in this project was to avoid exceeding the 30 meters per second limit for the solid fuel conveying. We needed to take into account the pipe diameter as the biggest physical limitation. In this case, total equivalent pipe length was short, no longer than 20 meters, which was something good for our calculations. We didn't want to exceed the 30 meters per second in the conveying speed, as for this application, maintaining a laminar flow is critical to guarantee a stable and long enough flame size out of the burner, as it also plays a big role during the combustion and heat transfer process. Hybrid technology was a perfect fit for this application, as its internal configuration and higher rotation speed reduces air pulsations, making the air delivered smoothly and laminar. However, exceeding the air delivery into the pipe limit will cause a rupture on the Reynolds number and start making the air turbulent. We didn't want that, as it may result in an anticipated combustion and a shorter flame size that can even cause the burner tip to catch fire. Final decision was to use two D98S Delta Hybrid units with over 60% more volume flow capacity and 30% more pressure capacity. All calculations were carefully made to avoid exceeding the 30 meters per second of air velocity in the pipe. Let's review the key takeaways from this case, where we replace a Delta blower with a Delta Hybrid unit. First, 30% conveying capacity increase for coal or alternative fuels usage and 40% operational cost reduction, including energy savings for technology renovation and extended maintenance intervals using the hybrid technology. Second, increase laminar airflow delivery, which helps the stability of the flame and avoid burner tip to catch fire by giving more distance to the flame initial distance. And third, keeping the existing piping system having a chance of future expansion by just increasing hybrid speed and the solid fuel feeding valve. Successful operation of a rotary kiln in cement plants require an adequate source of heat that will first raise the kiln to the operating temperature of over 1400 degrees Celsius and will then maintain that temperature by compensating for the various heat losses occurring in the kiln system. The heat is obtained by the combustion of fuel, mainly coal, combined with oxygen in the air. To obtain a proper combustion, two requirements must be fulfilled. First, sufficient oxygen present into the mix with the fuel, and second, a constant and stable fuel supply into the system. Primary air, jet air, or combustion air, depending the region where you are, all terms means the same. Air supply for the primary burner in order to guarantee a proper combustion with a beautiful long and wide flame across the kiln that guarantee the most heat transfer into the kiln. Many variables are involved into selecting the proper equipment to deliver this air into the system, but there is one that definitely matters the most for the production process. Which one do you think is the most relevant variable? If you select option C, you are correct. Momentum or mass flow is the most critical variable as it defines the oxygen mass flow that will be delivered into the system to guarantee the proper combustion. Ambient variables such as altitude over sea level or ambient temperature can dramatically affect the momentum and in consequence the heat transfer into the kiln. In addition to this, combustion air is the only resource for cement plant operators to control the kiln temperature and adjust it when a bad quality batch of raw materials enter the kiln or a new fuel usage is required. AERZEN has been really successful to supply high quality advisory and reliable machines into this application, to the point that some of the major cement companies at a global level prefer AERZEN equipment for this specific application. In our customer cement plant, the situation was critical, as the existing blowers for the process were very close to their operational limit. Considering the burner replacement and additional production capacity, the volume flow variable range was very limited. Existing machines didn't have variable speed devices, and they were thinking to upgrade the blowers to a bigger size with more capacity. AERZEN engineers analyzed the situation and realized that the high-speed turbo technology was a perfect fit for the expected operational condition. Technical data is as follows. challenge in this case was related to increase the mass flow through the same pipe system from 5,350 kilograms per hour to 6,800 kilograms per hour of air. In this case, the application is also known as process air, basically because there's no pneumatic conveying of any material through the pipes. Only air is conveyed to feed the kiln. But if there's no material handled through the pipe, how is the differential pressure generated in the system? Answers goes back to the continuity equation, where the pipe diameter reduction at the end of the pipeline increases the speed and air turbulence to generate additional momentum and helps the combustion process. In this case, the most critical limit was given by the pipe diameter. We did want to increase mass flow and turbulence into the system, but having too much air through that pipe diameter could also choke the air output due to extreme turbulence. With the on-site conditions, the best possible options was to install a high-speed turbo blower, which gives a constant mass flow through a high-speed impeller, giving to the process reliability and the additional mass flow needed according to the pipe diameter. In addition to this benefit, AERZEN Turbo includes an unbranded variable speed device that helps control the system and the airflow in case of alternative fuel or a raw mixed material change entering to the kiln. This application helps the operator to control the process, same way you control oxygen supply when using a torch. Let's review the key takeaways from this case scenario where we replace a delta blower with the high-speed turbo technology. First, air speed increased with a variable speed device, which creates additional turbulence in the mass flow delivered, making the flame size bigger and robust. Second, footprint reduced compared to the previous technology, and maintenance costs reduced to almost zero as turbo technology is maintenance-free. Third, electrical energy consumption dropped by 30% compared to previous technology, and additional control of the process to handle different raw material batches and new alternative fuels. Thanks for joining us today in our interactive presentation. We hope you have enjoyed our journey through one of the most exciting processes in the cement manufacturing. If you have any further questions, I'll be happy to discuss it with you later. And make sure to contact your AERZEN entity in your region for any specific questions or local support you need from our team. Thank you. Expect performance. Expect performance. Expect performance.